This is the third robotic lecture of the CAM 810S course. The subjects of today are robot arm kinematics, robot arm design, and motors. The kinematics of the robot arm are determined by all moving parts except drive system and power transmission. The type, the array, and the number of axes. We distinguish two groups of axes: main axis for positioning and auxiliary axis for effector orientation. Look at the diagram to the left. Main axes are 1, 2, and 3. They are used for positioning. Axes 4, 5, and 6 are auxiliary axes for effector orientation of this vertical articulated robot arm. Axes are named. In a vertical articulated robot arm, axis 1 is called base, 2 shoulder, 3 elbow, 4 shoulder roll, 5 pitch, and 6 roll. As you can see, some of these names are derived from the human arm. A vertical articulated robot arm with 6 axes has got 6 degrees of freedom, 1 degree of freedom for each axis. Remember the definition of the term degrees of freedom. It refers to the freedom of movement of a rigid body in a three-dimensional space. In the diagram to the left, 1 is movements towards the left and towards the right, 2 forth and back, 3 up and down, 4 around the up and down movement, 5 around the forth and back movement, and 6 around the left and right movement. Let's now look at the design of the R, or rotary elements. Axes are also called joints. A joint is that part of an arm which connects two links, and it performs a rotative motion. This joint is an unaligned R joint. In this case, the shoulder roll 1 and the roll 2 are aligned R joints, whereas the pitch 3 is an unaligned R joint. And now to the T, or translatory elements. This translatory aligned T-axis performs a linear motion. It moves up and down. This transitory telescopic T-axis performs also linear motion. It moves forth and back. Telescopic means that two or more tubes of progressively smaller dimension, which are nested within each other, increase or decrease the length of the stroke. A robot arm must be designed in such a way that two opposing requirements can somehow be combined. The arm should be light in weight, but it should have a high degree of rigidity. A good stiffness to weight ratio can be obtained by hollow and ribbed structures. And materials like light metal, that is aluminum alloys, and synthetic materials. This arm link combines both. It has a hollow structure and it is made of carbon fiber reinforced polymer, CFRP. This arm was developed at the Technical University of Chemnitz in Germany. Other measures like light motors and collocation of motors in non-moved elements and power transmission from motors to axis through timing belts or toothed belts, and light and compact gear drives, harmonic drives, may also help to reduce weight. A rather special design is this vertical articulated robot arm for heavy loads up to 500 kilo. The heavy load of the outstretched arm is partly compensated by a counterweight, which you see to the right. Let's now have a look at the drive systems of robot arms. We start with motors, specifically DC motors. The stator consists of two permanent magnets. The rotor is equipped with several coils. The coils are connected to the commutator segments. DC current is conducted to the commutator by two carbon brushes, and this makes a DC motor. After this lecture, you may watch a YouTube video which shows how the DC motor works. DC motors have several advantages. Rotational direction can simply be changed by changing the polarity. They provide a high starting torque. High RPM can be obtained. Speed control can be obtained with pulse width modulation, short PWM. A slight disadvantage is that they must be coupled to a sensor for position feedback. A bigger disadvantage is that carbon brushes wear out and must be replaced. A stepper motor or step motor is a brushless DC electric motor that divides a full rotation into a number of equal steps. The motor's position can then be commanded to move and hold at one of these steps without any feedback sensor. After this lecture, you may watch a YouTube video which shows how the stepper motor works. This is a stepper motor which was opened so that we can see the inside. So you can see the coils, the windings, and we can see the toothed disc, which you will see very nicely in the YouTube video. Stepper motors have several advantages. No position sensor is required, no encoder. Position control is simple. And speed control is simple as well. Stepper motors are maintenance free because they are brushless. Stepper motors have also some disadvantages. They are relatively inexpensive, which is still an advantage. So the disadvantages is that the torque is limited. And in case of an overload, the motor loses steps and the position is out of control. Stepper motors may oscillate and get out of control as well. The best performance is obtained by a three-phase AC servo motor. It is similar to a conventional AC motor, but for variable RPM control, it needs a complex controller. And a feedback device, an encoder, is needed. After the lecture, you may watch a YouTube video on how three-phase AC motors work. Now, closed-loop control allows precise control of the angular position, of the velocity, and of the acceleration. It's clear that with all these extras, the three-phase AC servo motor is the most expensive of all three types. This is the end of the third robotic lecture. If you want to know more about the three types of motors, you may, as was mentioned before, watch the three YouTube videos.